Using machine learning to troubleshoot performance issues in one data center is challenging. It is even more challenging to operationalize the service for an extremely large number of deployments across the globe. My name is Chien-Chia. We also have Amitabha and Chen-Chun who will join the presentation later. On behalf of VMware's Performance Analytics team, we are going to present how we build performance diagnostic service for VMware's hybrid cloud software solutions. We are also going to share the challenges that we faced and the experiences we learned from operating the service. VMware has a very large number of enterprise customers who deploy our software-defined data center stack in both their on-prem data centers, also known as the private cloud, as well as the VMware Managed Cloud, VMC. According to some unofficial survey, the number one thing that customers care about after they buy a product is they want the product to be up, meaning they want the product to be available whenever they want it, and the product has to be available most of the time. The second thing that customers care about, guess what? It's performance, meaning the customers want the product to be up and running and meets their performance expectations. Performance issue has always been a very hot topic among our customer escalations. Our customers, the cloud administrators, really need help in order to determine if their data center is performing normally or not. If it doesn't perform normally, what are root causes of it? Most importantly, what are the solutions to the performance problem? Our technical support engineers, the TSEs who support our customers in the on-prem data centers, as well as our site reliability engineers who manage our VMC deployment. They also need this kind of help to ensure our products are always performing and operating as best as they are supposed to be. This problem is already very, very challenging, even if you just look at one data center. Now we need a solution that works for all the data center at global scale. There are easily thousands of this deployments. Each data center might have thousands of hosts. Each host might have tens or hundreds of VMs that are running multiple applications at the same time. It's extremely difficult to get performance troubleshooting at this scale. Traditionally, what we did was we wrote and maintained a lot of these manual threshold-based rules. However, these threshold-based rules, they have a lot of limitations. On one hand, it's very hard to get them right. On the other hand, even if you manage to get something right, it's very hard to keep them always right for all the hardware and software combinations across the globe for all the deployments around the world. Just to give you an idea how difficult it is. Let's say now we want to determine if the disk latency is acceptable or not. Say you get 1 millisecond for your disk. Is that acceptable or not? The answer is it really depends. It depends on your physical disk type. It depends on your workload. It depends on if you have other bottlenecks in your system or not. It depends on your system states and so on and so forth. For example, if you have an NVMe device and you are just issuing 4K I/O with 100 I/O per second, and there's no other contention in your system, but you get 1 millisecond, that's a huge problem because your NVMe device is supposed to be doing much better than 1 millisecond for this workload. Okay. However, if it were a regular SSD, for example, then also you are issuing very large I/O, 1 millisecond could have been the best you can get. So that is why maintaining these rules is not scalable, because there are way too many ifs, way too many expectations. We need a better way to attack this problem. If we think about it, VMware is actually at a very unique position where we have thousands of customers who buy our software and deploy in their data centers. Just imagine if these thousands of production deployments can stream their telemetry data back to VMware, we should be able to address this performance troubleshooting at scale problem in a more data-driven way, which hopefully can also be helped by modern machine learning techniques. This is exactly the reason why I decided to build our performance diagnostic service in VMware Analytics Cloud. It's an in-cloud service to provide performance issue detection and root cause analysis. By doing this, we have multiple benefits. First, we are going to provide unified user experience for both our on-prem customers and VMC customers because they are going to use exactly the same tool no matter where they host their data center. Most importantly, we can decouple the analysis intelligence from our product releases and product upgrades. So customers no longer have to wait for the products to be upgraded every 2 to 3 years in order to enjoy the latest benefits. Also, now that customers are sending data to us, we should be able to do proactive analysis to catch the problem early on, even before customers notice them. This will not only reduce the number of escalations, but hopefully can also reduce mean time to detect and mean time to remediate because we have a better way to do performance issue detection and root cause analysis. Next, we are going to discuss how we architect the whole solution and what are the challenges we faced and how we solved them. This picture shows the architecture of performance diagnostics service. It's mainly composed of 4 components. The first one is VMware Analytics Cloud and the performance diagnostics service that runs in it. Second component is everything related to machine learning, where our data scientists are doing all the data experiments with different machine learning models. The third component is our automated and continuous machine learning ops pipeline. The last one is our application and the mechanism how we consume the feedback provided by our users. Next, we are going to dive into the details of each component, and now we are going to hand off to Amitabha, who is going to discuss the first component.
Thanks, Chien-Chia. As Chien-Chia mentioned, one of the design decisions we took early was to implement the ML models and logic in our cloud. But that raises some very interesting design questions because now data has to leave the on-premise data centers of our customers and come to our cloud. This has to be done under a proper legal and governance agreement. In the case of VMware, the agreement is known as CEIP, which is the Customer Experience Improvement Program. Customers agree to send anonymized data about their hardware and software configurations and performance counter readings, etc., to VMware Cloud with the intention of getting added benefit to the products and services by sending this data. Now, this data is consumed by an Apache Spark based service, and then the ML models and logic is run against the data, output generated, and delivered back to the customers who can see it on their user interface. Alternatively, the results are sent to a service portal where solution engineers and service personnel can monitor performance issues on all their customers and proactively act when required. Let us quickly visit how the machine learning problem is formulated. The data consists of time series data of performance counter readings such as IOs per second, throughput, CPU utilization, and so on. There are easily thousands of counters for a single host across the entire stack. Now, given this input data set, we want to study 2 different problems. The first problem tries to detect performance anomalies, which means that is there a performance anomaly that can be detected in the data set. For this, data scientists experiment and develop different models, which is akin to anomaly detection. Now, the answer to anomaly detection is whether there is an anomaly or not. If there is an anomaly, we have to root cause the anomaly and identify the issue which is causing the performance anomaly. For this, we mainly use rules and the decision tree approach, which looks at different counters and decides out of a few given issues which is the real issue which can be identified in the data set. Once the real issue is detected, several remediation options are considered and those are presented to the user or to the support personnel. As mentioned earlier, our input data sets come from customers' data centers and performance counters, and therefore this is not labeled data, and hence we resort to unsupervised ML approaches. To verify the soundness of our models and algorithms, we have to generate some validation and test data. We do it in two different ways. One instance is manually labeling, where some of our in-house performance experts look at the data and mark it with labels, marking it with times where a performance issue was encountered. Some other sources of datasets are bugs or known issues that are filed. One more way of generating validation data is to use synthesized data, in which we run experiments and artificially introduce performance perturbations or issues, and then collect datasets, labeling them with the equivalent performance perturbations. That helps us generate many synthetic datasets on internal test beds, and that data can now be used for test and validation purposes.
Next, let's move on to how a machine learning model can be trained and used in our operation pipeline. The goal here is to provide a fully automated and continuous pipeline without human intervention. Since the model's performance highly depends on the input features, the first step in our pipeline is to determine what features to be used by the model. In hybrid cloud enterprise deployments, there are many system components and layers. They involve complicated interactions and generate tens of thousands of performance metrics, so the number of features in our scenario is extremely high. To determine what features to be used, the domain experts first provide some candidate feature sets, and our pipeline then try out all feature sets during the training process and select the one with the best performance during validation process. Our pipeline would also retrain the model if the candidate feature sets change. You may wonder why not trying out all possible of feature combinations instead of relying on domain experts' input. This is simply because there are way too many possible combinations given this extremely high feature dimension. Hence, the resource overhead can't justify the gains. We have also tried some dimension reduction solutions, but this approach does not work well because statistical relation does not necessarily mean consequential relations. Finally, why not combining dimension reduction and some feature engineering? This is simply because the performance gains doesn't justify the engineering cost. In the end, domain experts usually can identify some promising feature sets easily, which effectively help us reduce the search space in practice. Once the model's features are determined, the associated training data must be preprocessed before being used to train a model. This is mainly because some models are more sensitive to data distribution and perform better only under a certain distribution. Our pipeline offers several data preprocessing methods. For example, it normalizes data according to the common standardization technique or Box-Cox transformation. It could also filter outliers in the dataset by applying bandpass filter. Finally, it covers other common data curation practices like avoiding dividing by zeros. All these preprocessing methods can be chained together as a series of data transformations, and there could exist more than one preprocessing chains according to the permutation. Our pipeline automatically tries all permutations of preprocessing chains and select the best one during validation. Our pipeline provides multiple model types for prediction, such as regression, autoencoder, isolation forest, and principal component analysis. During the training process, we train for each model type with each feature set and each preprocessing chain. With the label dataset, we form a model ensemble that includes the best hyperparameters during validation process. In addition, our pipeline supports aggregation mechanism like boosting or majority vote by jointly considering the prediction results from all the model types. We use the percentage of correct predictions as the custom accuracy throughout the model training process in order to balance between false positives and false negatives in our scenario. The common accuracy metric F1 score, which is defined as the harmonic mean of precision and recall, does not work well due to the skewed distribution of the anomalies. Once the model is done with training, it is sent to the model store. Apart from the model instance, the model store also includes all the information related to this model, such as whether this model is being deployed or not, a unique model version number, the timestamp of model creation, the feature set used by the model, the preprocessing chain for the model, the measured accuracy of the model, and the dataset used for training this model. The performance diagnostic service then chooses the model for inference, either by the most recent model, the most accurate model, or even a specific model version in cases like rollback.
Thanks Amitabha and Chen-Chun for going over the first three components. Earlier we talked about one of the goals is to provide proactive support. Internally at VMware, we have a portal called VMware Support Insights. This is designed exactly for this purpose. It looks like this. It's basically a screen shows a list of the clusters from our current customers who sign up for CEIP and sending us the performance data. It's going to list if each of the cluster has run into performance issue or not, marked in red. Any of the VMware engineers, full-time engineers, have access to this. Of course, it's anonymized data. We only know the UIDs. The VMware engineer can click one of them and then see when did the performance issue happen. With all this information, the engineer will be able to tell and then figure out from live performance data that if this performance issue is a real performance issue or not. We expect the engineer to give us the feedback by clicking thumbs up or thumbs down. This feedback will be sent to our feedback DB. The same mechanism is also built in our vCenter UI, where any of our customers, our vCenter customers, will be able to also examine their own data center if there is any performance issue or not, and then tell us the feedback if they feel this is the real issue or not. Once the feedback sent to our DB, it's going to automatically trigger model retraining. However, we do not do automatic model updates into our production services. The models or the new retrained model still has to be examined by our data scientists and ML engineers. This is because we have to do certain QA work in order to handle some problems like performance drifting. So what is performance drifting? By performance, we refer to the performance of VMware's SDDC software stack. Its performance is changing all the time because there can be new features, there can be new bugs, there can be new improvements, etc. So the idea here is, based on our definition of anomaly, it should be pretty rare to happen in most of the cases. So if we monitor the issue detection rate of any of our machine learning models, it should look something like this, relatively flat all the time. There shouldn't be any sudden spike or dip because it should be nearly impossible for a lot of clusters to hit the same performance issue pretty much at the same time, the spike. Or a lot of customers all of a sudden they no longer hit this issue. It's also something very weird. It doesn't meet our definition of an anomaly. So I monitor this issue detection rate. When there is some changes, we have to take a look. Why do we have to take a look? Because this change can indicate two different things. One is it can be a good drift, meaning this drift is actually something expected. So all that we have to do is find a way to make our model learn the new behavior, such as we have more labels to reinforce the model so that it tries to find the right threshold or learn the right trend of the new normal rather than treating them as anomalies. Amitabha is going to next talk about the bad drift case where we have to take more sophisticated actions.
Thanks, Chien-Chia. So now let's examine the case of the bad drifts, which means that our models are noticing far more performance issues than were seen previously. This can be because of two reasons. First, it could be because of data drifts, which is not very uncommon in our setups. Performance data is coming from hardware systems and hardware changes all the time. So it could be possible that on some faster, newer hardware, performance data is very different from what our models have been trained on. In this case, this is a false positive, and therefore we have to figure out how to retrain our models using new data sets. A different kind of issue is when an actual performance issue has crept into our product line and our models are detecting this performance issue. This is, of course, a much more serious case and needs to be addressed immediately. I'll take an example of an event that occurred recently to show how our models performed and how we could detect and triage this issue. So, VMware has managed clouds which our customers use to have cloud based data centers. These clouds get OS software updates in periodic cycles. So, what happened was a severe performance vulnerability was checked in unnoticed in our top of tree branch, which was then consumed by the cloud systems. Therefore, this performance issue crept in, and then when customers started deploying based on that operating system branch, all those systems started encountering the performance issue, and our models correctly detected the spike in the number of performance issues that you can see on the right. So in this case, we have to look through the data, look through the performance issues that are being generated, and figure out the root cause because of which this event is happening. And in this case, we traced it back to the performance issue which was checked in into our code, and we had to quickly fix that issue, release a patch, update our operating system so that before customers actually saw the issue which was being encountered in their systems and reported it and thereby causing an escalation, we could go and quickly fix it and the problem was all resolved. That's another example where machine learning techniques can be very powerful in seeing and through vast volumes of data and figuring out an issue quickly, which would ordinarily be very hard for humans to do.
Now a quick recap on how we put together all the MLOps components in production. We have the VMware Analytics Cloud as our data lake and the data platform where we run performance diagnostic cloud service. Our data scientists and ML engineers constantly work on data experiments, monitor the issue detection rates, review the latest feedback to iteratively improve our machine learning models over the time. We also have the automated and continuous ops pipeline to automatically take care of the feature selection, data preprocessing, model training, retraining, model serving, model versioning, and model rollbacks. The feedback loop between us and both the internal and external consumers is extremely critical for our service to keep improving both the performance troubleshooting experience as well as the quality of the VMware software-defined data center solutions. So, what did we learn from this multi-year experience? Chen-Chun?
Looking back, we have learned a few critical lessons when carrying out machine learning-based performance diagnostic service in production. First, it is important to have a pipeline of continuous and automated model training and serving. Especially, a pipeline for automatic feedback consumption helps provide fresh training data and keep the production models up to date without human intervention. Second, monitoring dashboard in production help visualize the deployment performance for easier tracking and alerting. Finally, an orchestrated experiment environment helps us validate behavior with synthesized setup and data instead of messing up with the production.
This concludes our talk. We'd like to thank all the teams who worked together with us throughout this multi-year journey, including VMware Analytics Cloud team, the VMware Support Insight team, our research partners, Parishik and Udi from the VMware Research Group, the support from our management team, Rajesh, Bruce, and Chuck, and all the folks in the VMware Central Performance Group. Thank you for watching, and we look forward to meeting you virtually in the coming online discussion sessions.